going to last time, is that even if you have a whacked out, potential R, the spherical harmonics for the angular part are just a good, solid basis set, right? From separation
Anywhere in
variables.
that sphere, which some of the angles say, like, anywhere, as long as the R is that size, it's anywhere in that.
Yeah, I mean, if you think about it, what's nice about the separation of variables is that it's literally pulling out in the angular part, there is no R dependence, or vice versa. For your potential, if it's only a function of R, it has no angular dependence. Okay? All right, so what we've done is we've come up and we've got the angular part, and that's the spherical harmonics. And let's see. So the spherical harmonics, inside the spherical harmonics, we have Legendre polynomials and associated Legendre polynomials. Yeah. And so, again, I'll mention for homeworks, I asked you guys to do for homeworks the three-dimensional problem, particle in a box. All right, and I also asked you for homeworks to do from chapter 2, the delta function potential. Okay? Yeah, I asked you to do all the details of the delta function potential, the last thing in chapter 2.
Yeah, we had a homework from that section.
Okay, and you had some homeworks from that section too. I'm just kind of going over the things that I had in class. All right, so make sure you get those things in. The homework that I'd like you to do in this thing, we're now going to do, so now we're set up, we're going to solve for the radial part. All right, and right now we haven't even specified what the potential is. So we haven't said that it's really a hydrogen atom potential yet. All we've done is solve for a spherical problem where the potential is just a function of R.
We know the potential is a function of R.
Yeah, that's the only thing we know, but we don't know explicitly what that potential is. Everybody got it?
That has to be specified.
Yeah, it has to be specified, but as of now, it's any spherical problem. All right?
Right. As long as the potential is not a function of theta or phi.
I like Jeremy's pounding that, and I like it very much. Okay, so here are the problems that I want you to do. Okay, so in this section, we're going to finish up the radial part, just so you know where we're going. We're going to finish up the radial part for a couple of cases, but in particular, we're going to solve the radial part for hydrogen. All right, and then what we're going to do is we're going to tie the whole formalism for hydrogen into what we've been doing all through chapter 2, which was my goal to jump into chapter 2. All right, and then what we're going to do is we're going to go back and look at chapter 3 and kind of do a little bit of the matrix formalism. All right, and then we'll come back to this after we do that. So here are the problems through the hydrogen atom. Problems 4.13, part A only. Problem 4.14 and problem 4.15. Oh, sorry, and problem 4.16. That's it. And then we're going to go back to chapter 3.
So 15 and 16?
Yeah. All right. And then the last thing I want to mention is I forgot, Matt reminded me just now, is that we have class. Oh, so I would like to have class, a makeup class next Monday.
Next what?
Next Monday.
Oh, not tomorrow.
No, yeah. So I would have told everybody to work tomorrow for sure. But next Monday. So I'm free after say 1 o'clock on Monday. So I could do it during the day, but I'm also free to have it Monday evening, like 5, 6, or 7, something like that.
Till 1?
Let's do it for 2 hours, all right?
All right.
I like earlier, but
I think earlier too. I have to be D-Bane by 9 every Monday night. So.
Okay. So how about if we did it, can anybody do it at 4 on Monday?
Yeah.
I think so.
4 o'clock, Jeremy? Does that work?
4 to 6.
Yeah, Matt?
Anytime, 4 a.m. or 4 p.m.
Okay, so 4 p.m. looks like it works. We'll go 4 to 6, all right? Occasionally I can get a pizza, but I haven't arranged to get pizza for you guys. So I'm not bringing in pizza this time. All right, but you guys are free to bring pizza for
Just
yourselves.
coordinate it so not everyone brings pizza.
Yeah, so if you somehow want to, so the only thing is I haven't got department money for it this time. But if you guys want to make some type of coordinated effort so that pizzas show up or something like that.
Chespin's is not what it used to be.
Really, I mean, everybody loved the buffalo chicken and got me hooked on the buffalo chicken pizza there, which is
Yeah.
good. But anyway, I'll let you guys
No, it's
decide
good.
that.
No, the cook's gone, and you guys,
But I'll let you guys decide that if you want to do that. But if you do decide to do that, then please let me in on it and I'll put in some money. Alright. Okay, so is everybody clear on what we're doing?
Yep.
Okay, so let's start. Alright, what we ended up with finally is that we're solving some spherical problem. So some spherical problem. And we started out h psi equals IH partial psi with respect to t. This is the time-dependent Schrödinger's equation. We're going to do separation of variables right away between the spatial coordinates and the time coordinates, right? And we'll pull out a time coordinate. G of t equals e to the minus I e n over h r t. And that leaves us with the time-independent Schrödinger's equation. And because it's in spherical coordinates, we're going to do r, theta, phi. And we're anticipating that there'll be an infinite number of solutions because we're doing separation of variables. And so we're going to end up with en psi of r, theta, and phi. Okay, so we did it. We went through everything. And we went through the separation of variables, and Griffiths does an outstanding job at it. We'll work through it. We've done it enough ourselves. I asked you to do it for homework, for the infinite particle, for a particle in an infinite cube. All right, so you should be well aware of how to do that. What you end up with is a function of theta plus a function of phi plus a function of r all equals 0. What happens is you combine these together into one function of theta and phi, plus f of r equals 0. Oh, let me point out here, for v equal f of r only. So this is a big thing. So we're solving this problem for f of r only. And notice up here, I mean, these are nice things to remember for v, not f of t, right?
Right.
So we've got two big criteria in there that allowed us to get here, which is important to point out. Okay, and so what we just did is what we realized is that this has to be true, that this has to be a constant, and this has to be minus a constant. Although I think there's a minus in here. So I think this is minus a constant equals 0. All right, and then what we did for this constant, we let the constant be L times L plus 1. Is it L? I thought it was L plus 1. So L times L plus 1.
Yep, minus L times L plus.
Yeah, so 1 becomes equal to minus, and the other equals to positive. So a constant equals L times L plus 1. All right, and the first thing that Griffiths did, and I wanted you to go through this, is to solve for the angular part, and there's a lot of great stuff here. You've got to work through it all, but we get the solution for the function of theta and phi equal to, I think that was the minus case.
Yeah, that was the minus case.
That was minus equal minus L times L plus 1. We get solutions that are y to the L ml of theta and phi. And these are called?
Spherical harmonics.
These are called spherical harmonics. And they are therefore these beautiful, nice solutions for any spherical problem where the potential is not a function of r. Isn't that nice? So maybe you're doing nuclear physics someday, maybe you're doing particle physics someday, all right? And you're going to have to do Schrödinger's equation, all right? And, the potential is not going to be a Coulombic or just a Coulombic. And so, you might be able to use this as a starting point, okay? The properties of this are what? This is non-zero for,
That has to be not zero.
okay, well, yeah, so this is,
For any
this is true for L equals 0, 1, 2 to infinity,
And for ML,
and for,
from negative L less than or equal to
Negative
ML.
L.
minus L is less than or equal to ML.
Less than or equal to L.
All right? Now, what's cool about these are they themselves are normalized and form a complete basis set. In function space. Alright? Not too surprising. I mean, that's what we got for the infinite well. For essentially each dimension of our well was one dimension, and that one dimension gave us an infinite basis set in that one dimension. And so now we're in 2 dimensions, and so we've got that infinite basis set there. So what I'll do sometimes is instead of writing a spherical harmonic like this, what I'll use is a little bit of a complex abstract vector notation. All right, what I'll say this is equal to L, comma, ML. So this is a ket. This is a Dirac ket.
What do you create those?
Well, so what it is, it's an abstraction.
Did he create those though?
Oh, yeah. This is Dirac ket. So. All right, but remember, what the spherical harmonic really looks like is equation 4.32, and I wrote it down last time. It equals, I'll write it down over here because it's the same thing. It equals a whole bunch of stuff times e to the I m phi, p to the m, cosine theta, all right, and so what we're saying, Mike, is that, look, this is the function, this is the answer. But we're big enough to not have to write that down. It's okay if we just write down the letters, because what differs from one spherical harmonic to the next is simply which ML you put in and which L you put in. I should put an L there. By the way, it's my habit to put in an L there. Griffiths doesn't use it at this point. Yeah, he just uses M. And so what's going to happen later is that whenever you have an angular momentum, M is going to be a projection of the angular momentum. And so we're going to introduce lots and lots of angular momentums later on. We're going to introduce like spin. Spin is an angular momentum. And then we're going to have the projection of the spin. And so what I do is I clearly distinguish it right at the beginning. So I'm putting in that subscript right away. All right? But what we want to do, guys, is we want to graduate to this level of abstraction where we don't have to write down the whole form of the equation every time. We know what we have to do. We have to put in whatever L and ML we want. All right? Now, if this is a complete basis set in function space, all right, what if I did this? What if I did the integral of y to the L ML star of theta and phi, y to the L ML. Okay, I'm not done. I want you to finish this integral for me. But what do you think I'm getting at here?
It should be square normalizable. Well, it's
Okay,
a
square
probability
normalizable.
density,
Right?
and then that creates a probability density.
Okay. Okay, good. How about this then? Yeah.
Ability for you.
How about this? How about if I did L prime
Angle.
ML prime?
Where you go to the orthogonality of that, so you get the delta function.
Okay, so I like where Aldemar's going. So why would I get a delta function?
Because of the orthogonality of
Because they're orthonormal. Because I'm using these, I've got a complete basis set. All right, and so now what am I essentially taking? I'm taking what in function space? I'm taking the dot product in function space. All right, and so what is the dot product in function space called? It is a special name.
Inner product.
It's called an inner product. Matt, you look lost.
Oh, no.
You're cool?
Yeah.
You cool?
Fun.
So this is so cool, it's boring.
Just not that.
What in the bra direct notation?
Yeah.
It's L, little L,
No, L comma.
L comma ML.
Yeah.
L comma ML.
So what I'm doing, I'm kind of graduating to this idea that as physicists, we don't like to write down all this stuff.
Right.
So we want to go to this abstract idea.